All right, in this video, we are going to continue on with our talks about linear transformations, and we're going to in chapter 1 by talking about how to take a linear transformation and make it into a matrix that we can actually use. In the previous video, we dealt mostly with just single vectors. So we had one matrix A, and that you had your vector X, or it changed into a vector U, etc. But how do you write an actual entire linear transformation as a matrix? We're going to look at the basics of that, along with a couple of definitions here in this video. So first little housekeeping thing is that remember that a linear transformation that maps the nth dimension into the nth dimension is actually a matrix transformation that maps X into AX. That comes from the idea that, remember, right now we're saying transformations are going to be matrix multiplication. To find a formula for T, we consider columns of the identity matrix of Rn. So for the first time, we are looking at what we call the identity matrix, which we will see a number of times in this class. An identity matrix is just, first off, it is a square matrix, which means that the rows and the columns match. So however many rows you have is how many columns you have to have. You'll have the number 1 down what I call the main diagonal. So starting in the upper left, all the way down until you get to the bottom right will be the number 1, and every other element in this matrix is a 0. So going forward, that's what I mean by identity matrix. So now T is determined completely by what it does to the columns of the n by n identity matrix I sub n. So if we let the vector E sub n denote the nth column of the identity matrix, then the linear transformation of T can be defined as the following. So remember, once again, T of X and A times X are the same thing, all right? We all know that vector X is just a column vector that you're going to be multiplying by. So we'll let that be a dimension of whatever needs to be suit your problem. What we're going to assume here is that for matrix A, we're going to let, and once again, these are all columns. Each column of matrix A is going to be denoted by you transforming the columns of I sub n. So that's the notation we use here of T of E sub 1. When you transform the columns of an identity matrix, you are getting the matrix A that will be part of your linear transformation. All right. So our theorem that we're going to use to kind of build up to the big definition at the bottom here is, let's assume that your transformation T is mapping from the nth dimension into the nth dimension, and we're going to assume that it is a linear transformation. So it meets those two criteria that we discussed in the previous video. If that is the case, if it's linear, then there exists a unique matrix A such that T of X equals A times X for every single X in the nth dimension. In fact, A is just the m by n matrix whose jth column is the vector T sub, the transformation mapped on E sub j, where E sub j is the jth column of the identity matrix. So kind of the same thing from the previous slide. When you apply the transformation to every column of the identity matrix, we are defining A in this way. Well, this matrix A, when you can find it, is going to be the big thing today. This is what we call the standard matrix for the linear transformation. That's going to be our goal to find first, is how do you write a standard matrix for a linear transformation? Because once we learn how to do that, I will end this chapter with a couple of definitions of what we can find from transformations, but we have to know how to find the standard matrix first. All right, so a couple different ways that I'm going to have you write standard matrices. So now, these are not considered the hardest ones that are out there. We'll see some more challenging ones after chapter 1. For right now, it's all about learning the basics. So in this first example here, if we let the transformation be mapping from the third dimension into the second dimension, and we assume that it is a linear transformation, then let's define T of E1 as 1, 3, T of E2 as 4, 2, and T of E3 as negative 5, 4. Then what would the standard matrix of T be? So now what you will notice is that if you want to write your standard matrix A, remember when you act a transformation on E, which remember E is the columns of the identity matrix, you are generating the columns of A. Let me go back real quick to the definition. Each of these represent columns of your standard matrix A. So when I go to write A, when it says that T of E1 is 1, 3, that's not a row. That actually becomes a column. So the first column of A would be 1, 3. Similarly, T of E2 would give you the second column of your standard matrix, and then T of E3 would be negative 5, 4. And this is your standard matrix of A. Now, very nicely, I'm not making you do the transformations right now. I'm kind of leaving that and kind of letting me do it for you and just kind of letting you give you the numbers. So remember, for chapter 1, we're going to make it very nice. Later on, I'll have you do your own transformations in this class. One other thing to note here that might help you check your answer now that we did example 1. Go back and look at the original dimensions here. Those dimensions that you're mapping will help you know the dimension of your final standard matrix. So if you notice, in this problem, we normally would call this a 2 by 3 matrix because there are 2 rows and there are 3 columns. But if you notice in your transformation, the number of the mapping is in the opposite order of how we read matrices. So going forward, whatever the first mapping is, so in this case, R cubed, that tells you the number of columns that you're going to have in your matrix. So that is where the R3 comes in. The dimension that you end up in, or where you finally fall, which in this case is R squared, that tells you the number of rows. So 1, 2 rows, that's where the R squared is. So if you read that backwards, the first number or the first dimension is the number of columns, the second dimension is the number of rows, and we know what answer we're shooting for. That's one way of doing it. The second way we can do it is I can give you the expressions of a matrix or a transformation and have you write the standard matrix. So number 2 says, write the standard matrix for the linear transformation that maps the second dimension into the fourth dimension. So remember already, 2 columns, 4 rows. We know that already. It's given by this expression. T of x1 equals x1 plus 4x2, 0, x1 minus 3x2, and x1. Once again, number of columns, and then this is the number of rows. So when I go to write my matrix A, I know that I'm going to only have 2 columns in this problem, but I need 4 rows. So I'm going to write a little bit of a longer matrix vertically for this problem. Each and every one of these 4 elements here give you the notation for the rows in your problem. So when it says x1 plus 4x2, the coefficients of those give you the first row of your matrix. That would be, oops, come on, pen. There we go. 1, 4. Since the second element is just the number 0, that means both of your elements need to be 0. Your third row is x1 minus 3x2, so that would be 1, negative 3. And then since your fourth element is just x1, that would be 1, 0. And that is the second way that we can express our standard matrix from a linear transformation. Now that we know how to write a standard matrix, this is the big thing in this section. How do we know if a transformation is one of the following two things or if it's both or neither? The two definitions we're going to cover now is the definition of a mapping or a transformation being onto, or a mapping or a transformation to be one-to-one. So let's go through each of these and then we'll do a couple examples to wrap up this video. If you have a mapping that goes from the nth dimension to the nth dimension, it is said to be onto Rm if each b in the final dimension is the image of at least one x in Rn. All right. So using your visual here, what that means is that in this first picture, since there are elements in the nth dimension that do not come from the domain, remember, because everything in the domain maps into the range. Since there are elements that are in the codomain that are not part of the range, that would be an example of not onto. Versus in my second example, since there's nothing extra and it's easily seen that everything in the domain maps into the range, that would be an example of onto. Everything over here, if I pick any point or any vector in this range, you will get back to the domain. Over here, remember, there are plenty of spots that are part of the codomain, but not part of the domain. Another way you can think of it as well is that T will be not onto when there is some B in the final dimension for which T of X equals B has no solution. So if there is a B in the final dimension that you get an inconsistent solution, that's another way to verify not onto. The other idea we can talk about is the idea of one-to-one. A mapping is considered to be called one-to-one if each B in the final dimension is the image of at most one X in the nth dimension. Now, where this is different here is that if you look, it doesn't matter that there's extra space when you're doing one-to-one. You can have parts that aren't going to map into. That doesn't matter in one-to-one. Instead, every vector that is in the range, so in this case, I have two vectors circled. Each of those vectors can only come from one vector in the domain. Unfortunately, in this one, these three vectors map to that first vector, and these three vectors in the domain map to the zero vector. Since more than one vector maps to an element of the range, this is an example of not one-to-one. Versus if you look at the second picture I have, we have 6 vectors in the range that we're worried about. And you notice that each and every one of those vectors comes from a separate vector in the domain. So once again, if every vector in your range comes from one vector in the domain, you have a one-to-one linear transformation. Now, obviously, the problem here is that if you're working in higher dimensions, this is impossible to draw and visually see. So we need a way to be able to use our properties to know whether or not each one is true. So here's kind of my big theorem to wrap up this section. If you have a transformation, if you have a transformation, and we're going to consider once again that it is a linear transformation. Step number 1 is you need to find the standard matrix for T, because you need A to do these two parts of the theorem. Once you find the standard matrix, the following is what we're going to do. We can say that the transformation maps Rn onto Rm if and only if the columns of A span the nth dimension. This comes from a theorem that we saw, I believe it was back in section 1.4. This will only be true if there is a pivot position in every row. So go back to the video, I believe it's section 1.5, and we did some examples of how do you know the columns of A span an entire dimension. That's only true if there's a pivot position in every row. What we're going to claim in this section is that if you can find a pivot position in every row, your mapping is onto, or your transformation is onto. If you want to see if T is a one-to-one transformation, what you will have to do is this will only be true if the columns of A are linearly independent. Now, when it comes to showing if columns of a matrix are linearly independent, there are the shortcuts that we've learned in section 1.7. If those show up, if you're not able to use one of the shortcuts, remember what you do is you set up the homogeneous matrix equation, and if there is no free variables, this implies linearly independent, which for us, linearly independent will mean one-to-one. If there is a free variable, and there can be more than one, doesn't really matter, that means you have linearly dependent columns. And for this section, linearly dependent means not one-to-one. So what we're about to do is do a couple examples of where we're going to work out whether or not a transformation is onto or one-to-one by finding the standard matrix and checking these two criteria. So example number 3 for this video. Determine whether the following transformation is one-to-one and or onto. So step 1 I'm going to do is I'm going to write my standard matrix. So my standard matrix, remember, I can verify columns, rows. Since they're both the same number, that kind of helps you out a little bit. We are going to have to draw a 3x3 matrix. Remember, columns, rows. So each of these expressions that I have underlined represent the coefficient of the 3 rows of your standard matrix. So if I plug these in based on my coefficients, your first row will be 1, 3, 0. Your second row will be 0, 3, 4. And your last row will be 0, 0, 4. And so that's the first thing we need. It technically does not matter which one of these you do first. Usually when I teach this, most students like to do onto first, and let me show you why. If you want to show whether or not a matrix is onto, all you have to do is you're going to take the matrix that you've just found, and the question becomes, is there a pivot position in every row? Which means that only requires you to go into reduced echelon, I'm sorry, not reduced, just into echelon form. Now, if you notice, this matrix is already in echelon form. I did that on purpose to kind of let you see this. As I circle them, hopefully you recognize that there is a pivot position in every single row of the echelon form of this matrix. So immediately I can answer the second part of this question. Is it onto? Yes. And if it ever asks you the reason, it's because there is a pivot position in each row. And that's the first answer to this question. The second thing you want to do is we have to talk about one-to-one. So unfortunately, none of our shortcuts happen here. So kind of reviewing those shortcuts. There's more than 2 columns, so you can't use the multiples rule. There is not the 0 vector, so we can't use that rule. And then there's not more vectors than entries, so we can't use that row. So the only way to solve whether it's one-to-one is I need to take my standard matrix and I'm going to add the 0 column on the end to set up the homogeneous equation. So now your job is to figure out, is there a free variable or not? So let's see, looking at this, first thing I would do is I would take row 1 and subtract row 2 because the first column's good. I'm just trying to get rid of that 3 in the top of the second column. So that would end up being, not 0, end up being 1, 0, -4, 0, and then we'll leave everything else alone. So we have our first 2 pivot positions. My third pivot position is that 4 at the bottom of column 3. So I need to get rid of the 2 numbers that are above it. So I would take row 1 and add row 3. I would take row 2 and subtract row 3. and you should end up with 1 0 0 0 0 3 0 0 0 0 4 0. And as you can see from right here, you don't really need to go any further now that you've gone to this extent. You've got the 3 pivot positions. You did not end up getting a row of all zeros. So in this case, there are no free variables, which implies that this transformation is not, I'm sorry, it is, let me rephrase that. I wrote the wrong thing. Since there are no free variables, this implies linearly independent, which for us, if it is linearly independent, it is yes, 1-to-1. So no free variables means linearly independent. We learned that back in section 1.7. Now that we're showing linearly independence, we can say that it is a 1-to-1 transformation. So in this example, the original transformation is not only 1-to-1, but it is also onto. All right. A second example, let's do one that doesn't map into the same dimension. So what about number 4 here? If we want to do a mapping from the 4th dimension into the 3rd dimension, it's labeled by the following. So T of x1, x2, x3, x4 is x1 minus 4x2 plus 8x3 plus x4. Then 2x2 minus 8x3 plus 3x4. And finally 5x4. So I need to write my standard matrix to get started. So we're going to have 4 columns and 3 rows here. And so remember, each of the expressions over in the second part of your transformation, those represent the rows of your standard matrix. So we're going to end up having a row of 1, -4, 8, 1. Then a row of 0, 2, -8, 3. And finally, a row of 0, 0, 0, 5. All right. So in this case, all right, if I do my onto again, this just requires you to be in echelon form, which it looks like, as I rewrite the matrix just to be in a different color here, it looks like you are already in echelon form because you have pivot position, pivot position, pivot position, and everything below those is a 0. All right. So back to my original point. If a transformation is onto, there must be a pivot position in every row. Since there is a pivot position in all 3 rows here, the answer is yes, it is onto, because once again, there is a pivot position in each row. Very good. All right. Coming down to the 1-to-1 part. So in this case, I'm going to do this one a little bit differently. And I'm going to talk about the way you could do it, but I'm going to do it with one of the shortcuts because I noticed that one of them works. All right. So obviously, if you don't recognize the shortcut when you're doing these problems, that's okay. You don't have to recognize it every time. What you could do is you could once again put the 0 vector on the end. All right. You could put it into reduced echelon form and figure or not if you have any free variables in this problem. What I'm going to do instead is I'm going to remind you about one of your shortcuts that might allow you to go a little quicker. In this case, each of these columns represents a vector. So you've got 1, 2, 3, you've got 4 vectors. Each of the vectors has 3 entries. If you look back at the very end of section 1.7, if the number of vectors is greater than the number of entries, this immediately means that your columns are linearly dependent. And for this section, if you show me that the columns of a matrix are linearly dependent, that means that the transformation is not a one-to-one transformation. So that's the way I noticed it. Obviously, if you add the zero column to make it a homogeneous equation and you do your row reduction, what should happen is you should find now that there is at least one free variable, and thus that also shows linearly dependent and thus not one-to-one. So that ends section 1.9, and actually that ends chapter 1 for this class. So in this first chapter, we covered a lot of definitions and a lot of what we consider basic linear algebra information. Everything we learned in this chapter, I like to tell students that we just did all the foundational work. So if you go back and as we go through this class, if you ever run into an issue where you're struggling with one of the foundational steps that we have to use, go back and rewatch these videos to get that idea down. As we move into future chapters, we will expand upon some of the foundational stuff. We'll do a little bit more with row reduction. We'll start looking at some stuff that is not row reduction in linear algebra. So a lot of stuff to come, but congratulations, we have just finished chapter 1 for this course.